I've spoken a lot about second order linear homogeneous differential equations in abstract terms, and how if, G is a solution, then some constant times G is also a solution, or if G and H are solutions, then G plus H is also a solution. Let's actually do problems, because I think that will actually help you learn as opposed to help you get confused. So let's say I have this differential equation. Y, the second derivative of y with respect to x, plus 5 times the first derivative of y with respect to x, plus 6 times y is equal to 0. So we need to find a y where, 1 times its second derivative plus 5 times its first derivative plus 6 times itself is equal to 0. And now let's just do a little bit of, take a step back and think about what kind of function. Most functions, if I have the function and I take its derivative and then I take its second derivative, most times I get something completely different, right? Like if y was, if y was x squared, then y prime would be 2x, then y prime prime would be 2, and then to add them together, you'd say, well, how would my x terms cancel out? So that you get 0 in the end. So, draw back into your brain and think, is there some function that, when I take its first and second derivatives and third and fourth derivatives, it essentially becomes the same function. Maybe the multiple time is the constant in front of the function changes as I take the derivative. And if you've listened to a lot of my videos, you'd realize that it probably is what I consider to be the most amazing function in mathematics, and that is the function e to the x. And in particular, maybe e to the x won't work here. You could even try it out, right? If you did e to the x, it won't satisfy this equation, right? E to the x, you'd get e to the x plus 5 e to the x plus 6 e to the x. That would not equal to 0. But maybe y is equal to e to some constant r times x. Let's just make the assumption that y is equal to some constant r times x, substitute it back into this, and then see if we can actually solve for an r that makes this equation true. And if we can, we found the solution, or maybe we found several solutions. So let's try it out. Let's try y is equal to e to the rx into this differential equation. So what is the first derivative of it, first of all? It's always useful to. So y prime is equal to what? Derivative chain rule. Derivative of the inside is r, and then derivative of the outside is still just e to the rx. And what's the second derivative? Y prime prime is equal to derivative, r is just a constant, so derivative of the inside is r times r on the outside, that's r squared, times e to the rx. And now we're ready to substitute back in, and I will switch colors. So y, the second derivative, that's r squared times e to the rx, plus 5 times the first derivative, so that's 5r e to the rx, plus 6 times our function, 6 times e to the rx is equal to 0. And something might already be surfacing to you as something we can do to this equation to solve for r. All of these terms on the left all have an e to the rx. So let's factor that out. So this is equal to e to the rx times r squared plus, 5r plus 6 is equal to 0. And our goal, remember, was to solve for the r or the r's that will make this true. And in order for this side of the equation to be 0, what do we know? Can e to the rx ever equal 0? Can you ever get something to some exponent and get 0? Well, no. So this cannot equal 0. So in order for this left-hand side of the equation to be 0, this term, this expression right here has to be 0. And I'll do that in a different color. So we know if we want to solve for r, that this, r squared plus 5r plus 6, that has to be 0. And this is called the characteristic equation. The r squared plus 5r plus 6 is called the characteristic equation. And it should be obvious to you that now this is no longer calculus. This is this is just factoring a quadratic. And this one actually is fairly straightforward to factor. So what is this? This is r plus 2 times r plus 3 is equal to 0. And so the solutions of the characteristic equation, or actually the solutions to this original equation, are r is equal to negative 2, r is equal to negative 2, and r is equal to minus 3. So you say, hey, we found two solutions, because we found two suitable r's that make this equation true, this differential equation true. And what are those? Well, the first one is y is equal to e to the minus 2x, right? R is minus 2. And then we could call that y1. And then the second solution we found, y2, is e to the, what is this? R is minus 3x. Now my question to you is this the most general solution? Well, in the last video, in kind of our introductory video, we learned that a constant times a solution is still a solution. So, if y1 is a solution, we also know that we can multiply y1 times any constant. So let's do that. Let's multiply it by c1. That's a c1 there. This is also going to be a solution, and now it's a little bit more general, right? It's a whole class of functions. The c doesn't have to just be a 1. It can be any constant. And then when you use your initial values, you actually can figure out what that constant is. And same for y2. y2 doesn't have to be 1 times e to the minus 3x. It has to be any constant. And we learned that in the last video, that if something's a solution, some constant times that is also a solution. And we also learned that if we have two different solutions, that if you add them together, you also get a solution. So the most general solution to this differential equation is y, we could say y of x, just to hit it home that this is definitely a function of x. Y of x is equal to c1 e to the minus 2x plus c2 e to the minus 3x. And this is the general solution of this differential equation. And I won't prove it because the proof is fairly involved. I mean, we just tried out e to the rx. Maybe there's some other wacko function that would have worked here. But I'll tell you now, and you kind of have to take it as a leap of faith, that this is the only general solution. There isn't some crazy outside function there that would have also worked. And so the other question that might be popping in your brain is, Sal, when we did first order differential equations, we only had one constant, and that was okay, because we had one set of initial conditions and we solved for our constants. But here I have two constants. So if I wanted a particular solution, how can I solve for two variables if I'm only given one initial condition? And if that's what you actually thought, your intuition would be correct. You actually need two initial conditions to solve this differential equation. You would need to know what, at a given value of x, what y is equal to, and maybe at a given value of x, what the first derivative is. And that is what we will do in the next video. See you soon.